Okay, so let's carry on. And the first thing I would like to remind you of, I gave you a slide about naming stars, in particular the names that we adopted from the ancient Greeks, the naming convention, namely brighter stars to dim stars, and we labeled them according to the letters of the alphabet. Pretty straightforward, not very creative, but that's life. One of the things I highlighted for you, though, at that point in time was this naked eye observation and how ancient Greeks simply went out and said, that star looks the brightest, I'll call that the alpha. Now, of course, this could have different meanings for different people in the sense of your eyes might be more sensitive to one color than another. So some stars might appear brighter than others, et cetera, et cetera. You can see where quantification would very much help out with this. So from the ancient Greeks, not only did we borrow their naming convention, but we also borrowed this system of what we call magnitudes. So the magnitude system. Ancient Greeks divided stars up into 6 groups according to how bright they were. And I call it golf score. Lower score, brighter star. So a magnitude 1 star are the brightest stars in the sky. These would be stars like Sirius, Betelgeuse, Vega, maybe even Regal. Okay. And then as you go down the scale, the star is actually getting dimmer to the point where a magnitude 6 star is at the limits of human vision. Okay. So the first question I have for you, and yes, I have questions. I'm just going to give you a second to read the question and then pause the video so that you can take some minutes to answer it. Feel free to restart the video when you think you have an answer. So the first question is just qualitative. And the issue is this. I'll read it out to you. Capella has an apparent magnitude of 0.06, while Nunki has an apparent magnitude of 0.023. Which appears brighter? Okay, good. Hopefully you pause the video, you've got an idea. But again, simple practice. I want you to remember that, hey, lower number means a brighter star. So this means that Capella of 0.06 appears to be brighter than Nunki, which is 2. And what we'll do now is we're going to go through and quantify, get an idea about how much brighter is that. Okay, that will be the future projection here. Okay. Also, the second thing I'll note is that right now I'm talking about apparent magnitudes. And you'll notice, okay, apparent magnitudes, that's because this is based on how bright a star appears to be. So we'll also have something about absolute magnitudes moving forward. So we're left with the ancient Greek system. We now fast forward, 1,800 years to 1800s, okay? And namely the idea about photographic plates. That allows us to start getting a comparison of how bright stars appear to be. I put my photographic plate up to the telescope, I record an image, and then based on how dark each star appears, if I'm thinking about negatives, so a bright object and a negative actually appears darker, I can start getting a better idea about how bright stars are, relatively speaking. So that being said, around the 18th century, we start quantifying. And we know from our records, our recordings of how bright stars appear, that the ancient Greek system, magnitude 1 through 6, corresponds to about 100 times difference in brightness. In other words, what I want to say is that a star that is magnitude 6 is about 100 times dimmer than a magnitude 1 star. Okay. So the next issue I have for you is that we would like to have some way of expressing differences between two stars. Okay, say magnitude 1 and magnitude 2. Remember, we're quantifying. I have 5 orders of magnitude. That's why I have the 5 here. And that corresponds, the equal sign, to a factor of 100. The question I have for you, take a minute, pause the video. What does x have to be? You got it? Okay, good. And so I'm sure you're already familiar. If you want to get rid of an exponent, we have to raise the number on the other side to 1 over that exponent. So if I want to undo this x to the 5th, one way to do it is a 5th root, if you will. So to undo something to the 5th power, you simply have to move it over to the other side in the exponent. We have 10 to the 2/5, and so that's what the value of x has to be. If we put this into our calculator and run it through, you get something that's 2.5. And I put an approximate sign in here. What does this mean? In the magnitude system, a star of magnitude 2 is 2.5 times dimmer than a star of magnitude 1, and etc. Star of magnitude 3 is 2.5 times dimmer than a magnitude 2. So each level on the magnitude scale represents a factor of 2.5 times dimmer or brighter, depending on which way you go. But wait, there's more. So that's just the first thing. That's the magnitude system. Now the issue is that we need to figure out some way to actually compare stars. Okay? So we're going to keep going a little further here. How do we actually assign a magnitude 1 or a magnitude 3, et cetera, et cetera? We don't want to do it by eye anymore. Okay? We're going to have to take a small little byline into, promise, logarithms. Okay? And I've actually lied to you, right? I've said logarithms in 2 slides, and then I realized I only did it in 1. So you'll forgive me for that. We've cut it in half. So right here, I just have a brief review of logarithms, and I'm hoping that you're somewhat familiar with them. So let me remind you why. Why do we bother with logarithms? Seems fair enough. And I've had you do this problem. I said, hey, if I gave you an unknown number, which I'm calling x, and raise it to the 5th power equals 100, what's the value of x? And you went through and you hopefully took a little bit of time on the calculator and figured it out. But there's another problem. There's a somewhat related problem that's a lot harder in my mind to solve. And that would be this problem. Let's say, for example, I take 5 and raise it to the exponent x and set it equal to 10. Set it equal to 100. That's a lot harder of a problem to actually solve. Okay? And that's exactly what logarithms have been designed to do, is to help us solve this sort of equation. We know how to do it if x is what we call the base, if x is the thing that's being raised to a power. What we don't have a very good idea on how to do is when the variable x is actually in the exponent rather than the base. Now, one way, of course, you could do this, and take a minute, just try to guess and check. What should the value of x be? Now, I don't need a specific value. Rather, what I mean is, can you give me a range of values for x in which the true value should lie? Go ahead, take a minute, see if you can come up with an idea. Good? Cool. And this is completely legitimate. I mean, this is what I would refer to as a guess and check method. So if you said x is equal to 1, you know that 5 to the 1 is less than 100. And in fact, x is equal to 2, 25 is still less than 100. Okay? So for example, 5 squared is 25, okay? But 5 cubed is 125. Okay? So right away, you know that the value of x should be between 2 and 3. Now, what value it is between those two, I don't know. We have to actually go through and calculate it out. Okay? So that's the whole point of having logarithms, is that it will help us solve an equation like this. Now, I should remind you of a couple of properties that logarithms have. You'll be taking advantage of these properties depending on what kind of question I ask you to solve. So the first property is what I say multiplication. So if you have a logarithm, now let me walk you through this. Okay? I have a and b represent numbers. So if I'm doing a multiplication of a times b, okay, that's what I have in here, and I'm taking a logarithm of that. Okay? And one of the nice things about logarithms is that it takes numbers that are being multiplied and turns it into addition. So instead of writing a times b and then taking the logarithm, you can write it as the log of a plus the log of b. Like I said, it's taking multiplication and turning it into addition. Now, related to this idea is how logarithms deal with exponents. Okay. So right here, again, I'll walk you through this, but notice now I've done a squared. Remember, exponents are a fancy way of writing repeated multiplication. So instead of writing a squared, I could have just said a times a. And then using this nice property of logarithms that take multiplication and turn it into addition, if I have a times a, that's the same thing as writing 2 log of a. So a shortcut for that would be anytime you take a number that's raised to an exponential, you can move that exponential in front of the logarithm. Just a different way of doing it. You're still applying this multiplication property. It's just that a faster way is to think of taking the exponent and putting it in front. Okay. So that's one property that I wanted to remind you about, and that's the one that we'll be using fairly frequently. The second property that comes up and is used fairly often is undoing the log. And again, I put in quotes. So just like how you can think of addition undoing subtraction, or you can think of multiplication undoing division. Those are, for lack of a better term, I'll say those are reciprocal operations. You can apply one to undo the other. Now, how you undo the logarithm? You look at whatever base it is. Okay, so here it's base 10. And if you raise 10 to whatever the logarithm is, that's how you actually undo the logarithm. Now you say, but wait, Greg, why do I have to raise 10 to the log of 10 log 10 of a? Can't I do it the other way? And I say, absolutely. The other way that you could do this is taking log 10 of 10 raised to a power. And then you can follow your exponential rule. You take the exponent, you drop it in front, and log base 10 of 10 is simply 1. Oops, sorry, missed it. Log base 10 of 10 is simply 1. So again, it undoes each other. Hopefully this is ringing some bells. You should have seen this at some point in, say, an algebra class. Probably said, why will I ever need this? Oh, it comes back. It's not by accident. So moving on, the magnitude system. In the 18th century, it was devised the method to actually compare stars quantitatively. Now I'm going to show you the equation how that astronomers use to compare stars. It's this. Let me walk you through it. On the left-hand side, what we have is the ratio comparing the brightness of two stars. So I've labeled it brightness of star 1 divided by brightness of star 2. So that's the left-hand side here. It's just a ratio. On the right-hand side, we have 10 raised to the 0.4. And that goes to the previous question about x to the 5th equals 100. Remember when we said x to the 5th, 5 orders of magnitude, is equal to 100, we got a value of 10 to the 2/5. 2/5 in decimal form is 0.4. And so 10 to the 0.4, you could put in there instead 2.5. So what we're talking about right here is simply the factor of brightnesses. Okay, so is it 2.5 times brighter, or maybe it's 5 times brighter, or maybe 7.5 times brighter? That's essentially what this side is doing. Okay. Now, because we want to preserve that magnitude system, we want to know how many times do I have to multiply 2.5 by 2.5 in order to get that ratio of brightnesses. So we have the brightnesses over here. We have this 2.5 raised to some number. And here, rather than doing the sum number, I've put little m of star 2 minus little m of star 1. And here I have to be very explicit. Little m does not represent the mass. Little m here is what we refer to as the apparent magnitude of the star. How bright the star appears from Earth. Okay, so anytime you see that apparent, how bright it appears to be from Earth. So we use this as the apparent magnitude of star 2 minus the apparent magnitude of star 1. Now, the interesting thing about this magnitude system that was developed by the ancient Greeks is that once we start quantifying using this comparison, we suddenly realize that there might be a bit of an issue. Namely this: what do we do with brighter stars? Of course, if we get dimmer stars, we can just add on 7, 8, 9, 10, yada, yada, yada. But how about up here? What happens if we find a star that's brighter than a magnitude 1? Probably already guessed it. We go to magnitude 0. But then, what happens if we get a star that's brighter than a magnitude 0? Probably got it already. We go to negative numbers. Okay. So unfortunately, we're locked in with this traditional system from the ancient Greeks. And how we've adapted it is that if we end up with brighter stars or brighter objects in general, then we just go to the negative numbers. To give you an idea about some of these objects, here we go. And we'll actually derive this one. The sun actually has an apparent magnitude of negative 26.7. Okay. Whereas a full moon, it's 14 magnitudes greater. Now, you know a difference in 5 corresponds to 100 times dimmer. This is a difference of 14. 5, 5, and 4. We'll round it to 5. Let's just say it's 15. That means it's 100 times 100 times 100 times dimmer. 100 times 100 times 100 is 1,000,000. So compared to a sun, a full moon is 1,000,000 times dimmer than the sun. All right, then carrying on. I've got a question for you. We're going to use this comparison chart, or this equation giving us the comparison of brightnesses. And notice I'm going to give you 3 pieces of information. So I've given you the brightness of Vega as it appears from Earth, the brightness of the sun, again, as appears from Earth, and I've also given you the apparent magnitude of Vega, which conveniently enough, not by accident, equals 0. So why don't you go ahead and take a moment and figure out what is the apparent magnitude of the sun? Go ahead. Alrighty then. And hopefully you see now why I decided to introduce the logarithms when I did. Because right now we have a situation where the logarithms are absolutely necessary. That is to say, we need to figure out the value of an exponent right here, what I've labeled ms, the apparent magnitude of the sun. So the first thing that I'm going to do, and you might have hacked away at it slightly differently, of course, as long as we kind of get to the same path, or excuse me, the same endpoint, it doesn't really matter what path you took. So here what I'm going to do is I'm going to take a logarithm of both sides of this equation. So, and notice again, I've decided to use log base 10. The reason for that is that when I use log base 10 applied to the right side of this equation, that 10 disappears. In other words, I can take just the exponent now. Now I've also converted 0.4 back into 2/5. That's more just for a matter of visual aesthetics. Okay? And now at this point, if I hand you this equation, you know how to do this. We have to multiply by 5/2 and rearrange the equation. So I've gone ahead, I've multiplied by 5/2, and here I've actually started substituting in the numbers. BS, come to think of it, that's not exactly a great subscript to use. I'll have to fix that later. The brightness of the sun, 1500 watts per meter squared. The brightness of Vega, and then over here I've put the absolute or the apparent magnitude of Vega. So we turn the crank and we pop out with a number of negative 27.1. Now, of course, you see from the chart on the previous slide, that's a little bit off from what I actually gave you. And the reason for that is primarily because I rounded this number to be a nicer value, the 1500. So we get a value of negative 27.1. In other words, the sun appears, so roughly 10 billion times more bright than Vega. Again, ballpark. Oh yes, and if you want, there's a pretty picture of Vega there for you, so we can ooh and ah over it. Now, it's not by accident that I chose Vega, and indeed, when we were doing this, when astronomers back in the 1800s were wanting to actually start doing this comparison, indeed, they actually chose a star with which to do the comparison. The original star they chose was actually Polaris. Finally, for once, they chose Polaris for something. The issue is that when they chose Polaris back in the 1800s and they did all the magnitudes, after a while they realized that Polaris actually changes in luminosity. We'll have to get to why that is, but they discovered that Polaris actually changes in luminosity, and so they had to pick a different star. That's why we actually do all of our comparisons with Vega now, is because it's been very consistent in how luminous it has been over the course of the last 2 centuries. Now, the next set of questions that I want to walk through deal with not the apparent magnitude, but rather the absolute magnitude. Right now, we have a measure of comparing stars with how bright they appear to be from Earth. But I would like to get a way of comparing stars when viewed from the same distance. So that's what we refer to as absolute magnitude. So this first step here is getting an idea about what we would refer to as the absolute brightness of the sun. So let me go ahead and pull that up. So I'll read this off to you and then send you running. The luminosity of the sun is 4.2 times 10 to the 26th watts. In other words, how much energy per second it emits. What is the brightness of the sun when viewed from a distance of 10 parsecs away? So I've provided some conversion factors here for you. I'll give you a couple minutes. Go ahead and hack through this. Got it? Good. So at this point, you have all of the information you need. We just need to plug and chug into our brightness equation. And so that's what I've done. I've substituted in the luminosity in the numerator. And then you'll notice in the denominator, I started off with 10 parsecs. There's 3.2 light years in a parsec. So that's the 10 times 3.2. And then over here, I've converted into astronomical units. How many astronomical units in a light year? And finally, how many meters are in an astronomical unit? So that's the 10, 3.2, the 63,000, the 1.5, and the 10 to the 11th. Now, as a highlight again, and just because you're online doesn't mean that you can make this mistake, don't forget everything inside the parentheses needs to be squared. So this whole number represents my distance, and so I have to square everything inside the parentheses. We turn the magic crank, and we end up with something like this. Excuse me. 3.6 times 10 to the negative 10th watts per meter squared. So keep in mind, this is when the sun is 32 light years away. 32 light years away, this is how bright the sun will appear to be. Okay. Now you notice I've actually labeled this brightness absolute. We as a society, or maybe I should say the astronomers, have decided to compare what stars look like from a distance of 10 parsecs away. When you're 10 parsecs away, that's the brightness. We call that brightness the absolute brightness. It gives us a way of making sure that we're comparing two stars from the same distance. Okay. So now we have the apparent magnitude of a star, and we have the absolute brightness of the star, the brightness as viewed from 10 parsecs away. The last thing that we need to do is get an idea about the absolute magnitude. And that's what the next question is here for. So, as a reminder, the apparent magnitude, lowercase m, of the sun is negative 27.1. What is the absolute magnitude, big M? Okay, so little m, apparent magnitude, big M, absolute magnitude of, okay? And that's, again, of the sun. And I've conveniently enough given you an equation. So I'll let you run that for a sec. Oh, excuse me. I should mention, excuse me. So prior, this equation said the brightness of star 1 and the brightness of star 2, and then the difference in those magnitudes of the two stars. But similarly, I can use that exact same equation for the same star viewed at different distances. So rather than saying star 1 and star 2, rather what I'm going to use now is the apparent brightness of the sun when viewed from Earth, and the absolute brightness. That is, again, the brightness when viewed from a distance of 10 parsecs. And rather than having the difference of the two stars now, I'm going to have the absolute magnitude and the apparent magnitude. So go ahead, take a second, hack through this, and when you're done, you can enjoy the nice little bubbling of the solar surface. Got it? Let's hack through it then. Again, we have the apparent brightness, the 1500 watts. That's from 2 questions ago. We have the absolute brightness, that's 10 to the negative 10th that we got from the past question. And we have the apparent magnitude. That was 3 questions ago, something like that. So let's take all that information and plug it together. So again, be careful. We have a minus and a minus, so they're double minus signs, so we have to put a plus in there now. And we need to get big M, the absolute magnitude, by itself. So we take the log, we multiply by 5/2, something like this. And then we have a minus minus, that becomes a positive. And when we move it to the other side, you end up with the negative. So there's our equation. Now we just have to hack away and plug it into the calculator. And you can see already, well, excuse me, I should say, you're going to get a really, really big number here. And when you take the log, it's going to make it, I don't know, a little smaller, for lack of a better word. And then subtract 27. So what we get at the end of the day is 4.5. So we think of the sun as being really, really bright. But when viewed from a distance of 32 light years, 10 parsecs, it is, okay, now we've got 27 orders of magnitude plus another 4. So now we're dealing with 31 orders of magnitude. So 6 times 100. So 6, I shouldn't say 600. What I want to say is 100 to the 6th, there we go, times dimmer when viewed from 10 parsecs away. Not very bright at all. Okay, so that's all I have for this video right now. But that's to give you a sense of where these absolute magnitudes come from. To rehash, We compare how bright the star appears with respect to Vega. That allows us to determine the apparent magnitude of the star. Remember, Vega we set as being apparent magnitude 0. Once we have the apparent magnitude of the star and we know how bright it appears to be, then we can go through and actually get the absolute magnitude of the star. We did that specifically for the sun, but there's no reason that we have to do it for that. We can do it for Vega, Capella, etc., etc.